Do you know which of the four resistors shown here would have the greatest overall resistance? Well, if you know resistance for a metal wire is equal to its resistivity times its length divided by cross-sectional area, then you've probably decided by now that this resistor has the greatest overall resistance. Simple enough, but what if a resistor was in this shape? What if the cross-sectional area was not uniform? So we could say the resistor has a length of L, and it's made of copper or aluminum or silver, whatever the material is, that will determine its resistivity. But as far as the cross-sectional area, well, one end, we'll say, has a radius of A, and the other end, we'll say, has a radius of B. So the cross-sectional area on this side is pi A squared, and the cross-sectional area at the other end is pi times B squared. Now you might be tempted to say that the resistance is equal to the resistivity times the length, the resistivity times the length, divided by the average area, which we would say is pi A squared plus pi B squared quantity over 2. It's not a bad guess. And in some cases, as long as the difference between A and B is not too large, it might be a decent approximation. However, it's not really correct. So how could we figure this out properly? Well, let's do something like this. Let's take a slice. Now, if we put an x-axis here, we say the slice has a thickness of dx. And if dx is really small, then for all practical purposes, there's no difference in the area on the right side of the slice compared to the left side of the slice. So we could say dr, the little bit of resistance of this slice, is rho times its length, which is dx, divided by its area, which would be pi, and we'll just say this is neither A nor B. We'll just say the radius here is some value r, so divided by pi r squared. Now wait a minute. We're referencing an x-axis. Let's show where the origin is. If I were to extend this line and this line, eventually they'll meet up. Let's try this again. Yeah, extend these lines until they intersect. Okay. There's our x-axis. So here's the origin. X equals 0 back here. Now you can probably guess where we're going with this. If that describes the resistance of this little slice, then we can build this kind of cork-shaped resistor out of several slices all placed together end to end, so that the total resistance is the integral of rho dx over pi r squared. We can take a couple things out of the integral sign. So resistance is rho over pi times the integral of dx divided by r squared. Now what are our limits of integration? We've got some value of x naught, and then some value of, let's say, x final. Okay, so we got to go from x naught to x final. Although we might change variables. We'll see. Anyway, we clearly have two variables, both r and x, right? Let's pick a slice here. The radius of that one is definitely less than the radius of the slice we highlighted, so as x changes, r also changes. So that's really the trick here, is to try to get r and x in terms of one single variable. Well, let's introduce an angle right here we call theta. Now it doesn't matter which one of these slices we look at. Let's take a look at this first slice. Whatever the value of x happens to be for that particular slice, tangent theta, tangent is equal to opposite over adjacent, yeah, so tangent theta would be equal to r divided by x. Or in other words, x is equal to r divided by tangent theta. Okay. If we look at the first slice of resistance that was indicated, we can also make a right triangle there, but you notice it's the same value of theta. That doesn't change. Essentially, as r gets bigger, x gets larger proportionally. So if we make a substitution, dx is just 1 over tan theta times dr. So step 3, our resistance is equal to rho divided by pi times the integral of 1 over tangent theta dr divided by r squared. And now our limits of integration, instead of expressing them in terms of x, we can say, what's our very first slice? Well, the very first one has a radius, as we indicated earlier, of a, and the very last slice we have to account for has a radius of b. So those are our limits now that our single variable is r. So r is equal to rho divided by pi tangent theta, the integral as r goes from a to b of r to the negative 2 dr. So the integral of r to the negative 2 gives us negative 1 over r. Let's change the negative to a positive and flip our limits of integration. So the resistance is rho divided by pi tangent theta of 1 over a minus 1 over b, where r is equal to rho over pi tangent theta b minus a divided by ab. Wait a minute, tangent theta, in the initial setup of this problem, no angle was stated. All we were given to start with was a length and 2 radii. Well, the angle can be determined as long as we know those quantities. Let's see. How about I draw this right triangle? Now we know this side is L, and this angle theta is just repeated again right here. What's this little distance? Well, that would just be b minus a, correct? Tangent theta is opposite over adjacent, so we can substitute in place of tangent theta b minus a over L. So our resistance is equal to rho times L divided by pi times b minus a, all times the quantity b minus a over ab. Now didn't that work out nice? B minus a cancels, and lo and behold we get a result that the resistance is rho times L over AB. How about that? A pretty simple result. Now, we should check to see if the result holds up for some special cases. Well, how about the case in which there's no difference between A and B? In other words, A equals B. Well, in that case, then we would just have, oh, sorry, I left out a pi here, didn't I? My bad. Okay, fix that. Anyway, if A and B are equal, then we might as well just call them R. And the resistance is equal to rho times L over pi AB, or pi RR, or pi R squared. Pi R squared is just the cross-sectional area of a circle, and we get R equals rho L over A, just like we would expect. So, yeah, that seems to be the case. If a resistor were in this bizarre shape, the resistance would be equal to rho times L over pi times AB.